together, right? And what it gives you a chance to do is figure out how I take the things that you guys have been working on, like your homework, and how I convert that into an exam. Because otherwise you wouldn't know until after the first exam. But then for some people, I'm too late. On my exams, what I typically do is I have a couple of bonus problems. So each problem, I try to make it such that the problem will take you like maybe 5 minutes if you just do it very, you don't rush through. You just methodically, step by step, go through the problem. It should take you 5 minutes. But of course, if you get stuck, it's going to take you longer than 5 minutes, right? If you go fast, you can go faster than 5 minutes. But it's a 50-minute exam, so I'll give you 10 problems, 10 5-minute problems. Now, of course, 5 minutes, that's subjective because, not everyone does the same problem at the same speed. Some people go faster, some people go slower. And so, and it's hard to judge because some problems, it may be a 5-minute problem to one person, but it's twice as long, and then the next problem is easier for that person, but twice as long for the next person. So it's average, I guess. But if you can finish these problems really fast, like if you really know the stuff, and so you're really quick with it, then there are some bonus problems. I give you like 2 bonus problems that you can take. So there are 12 problems total. 10 regular problems, okay? And they're 10 points each, so that's 100 points. But if you get like one of those problems wrong, you can easily make up for it by answering one of the bonus problems and getting one of those problems right. Typically, the bonus problems are a little harder than the regular problems, but again, that's subjective. You may think that the bonus problem is like super easy because you understood that concept very well enough. But typically, that's the case. So yeah, it is possible to get 120 points, 120 percentage points on the exam. It is possible. And if you did that, that would actually help you for the next exam if you really screwed up some, like if that was like a really bad day for you, right? That would help out. Okay. But for those of you who are trying to get an A in the class, then what you want to try to do is get on average 90 points for each exam. Okay, so the next thing we have to do is figure out when on this weekend right here is the best time to have our practice exam session. So, so by show of hands, who cannot make it on Sunday? Okay, I see a couple of them. Who cannot make it on Saturday?
We have a home game on Saturday too.
Huh?
There's a home game on Saturday, so I don't know if this building's open.
Well,
I think
yeah, we don't
runs by lock Saturday.
Locked on Saturdays.
Especially not at Auburn.
Nope, unfortunately.
Okay, so
Sunday.
so for the people who can't make it on Sunday, would you even want to come in if you could make it on Sunday? I mean, because like some people, not everyone shows up for the practice exam on the weekend. Yeah.
I can record it.
Huh?
I can record it.
Yeah, that's true. So for those of you who can't make it on Sunday and you would like to come on Sunday, would you mind seeing a recording of it instead? You guys are okay with that? Anyone not okay with that who can't make it on Sunday?
What time?
Well, yeah, no, that's next. That's another issue. Okay, so
Everyone gets wasted on Saturday.
okay, so great. We have Sunday down. Now we define the optimal time. So, are there any suggestions about a good time?
1 o'clock.
1? Is that good for everyone? 3?
One. 3 o'clock.
2. We in the middle? Okay, so how about 2? Who cannot make 2 because of some obligation?
How long will it be?
Well, idealistically, it should be an hour, right? If I can't do it in an hour, then I wouldn't expect you guys to be able to do it in an hour, right? and I'm not like super fast at solving these problems. So idealistically, it should be an hour. However, there's going to be questions, right? Well, someone will ask, how'd you do that, or why did you think of doing this? That kind of thing. So it could be an hour and a half, depending on how many questions. Okay. So it looks like it's 2 o'clock, right?
Yep.
Okay. So 2 o'clock Sunday. Yes.
Will it be in this room?
Mm-hmm. Yeah. Yeah, typically, and I'll double check, but sometimes during the weekend, someone will reserve the room for some kind of activity, so I'll need to double check that. And if I find out that this room is occupied, then we'll like meet over in the sister room over here or something like that. But I'll email you guys about it. Okay, great. Is there any question about the format of the exam? Like how that's going to go?
What is the format?
Huh?
I take it it's not multiple choice.
I mean, there may be some problems where it would be good to have multiple choice, but the whole exam as a whole, in general, is not going to be multiple choice. It's going to be workout. And the reason why is because, you guys get partial credit, So I'm more concerned with your ability to analytically solve the problems, and I'm less concerned with your ability to, if you know how to work your calculator very well, right? Because I've seen some people where they do everything right mathematically, except they'll key those numbers into their calculator, and for some reason they added when they should have multiplied on something, or I don't know, a negative sign, make it from their paper into their calculator, and so they write it down and keep on going, right? But it is possible that they get full credit if I see what they've done and what they've written down is correct. The calculator part, if that is wrong, they're not going to be penalized for that, right? But of course, for me, like when I'm grading, because I have like maybe 60, 65 things papers to grade, exams to grade, multiply that by the 12 questions. So that's a lot of problems, and so so the thing is that it's easier for me just to look at the answer and say, oh, they got that one right, and keep on going. If they got it wrong, then that forces me to check their analytical result to see what partial credit I can give them. Right? Yeah.
What's your stance on programs we write for our calculators?
Well, yeah, here's the issue with that. If you have a really nice program for your calculator and you get the numerical answer wrong, then it's difficult for me to figure out, give you partial credit.
Can we use them? Yeah, like we would just sacrifice partial credit ability. Can we use them?
Well, yeah, that's an interesting question because I guess the question is how are you demonstrating your mastery of the subject to create an algorithm that does what it's supposed to do, that you program to your calculator? That is a really good demonstration that you know what you're doing, right? Too, just as you would be writing it down. Now I guess the question is will everyone that has that kind of algorithm, that they program it themselves, right? And they're just putting in numbers that someone else did, but they don't really understand themselves. So I would say, without me knowing that, then I think the best thing to do is still write down the algorithm that you're going to use, right? But if you have like a really nice algorithm that you got from somewhere else, or you made yourself and you want to plug it in for the answer, I don't see anything wrong with that, but I still would like to see the algorithm. So to really prove to me that you really know analytically what's going on. Yeah. Yeah, because, and also this, for, not today, well, not today, but usually like a long time ago, before we had those calculators with those kind of abilities, if someone just handed in an exam that had nothing worked out with all the right answers, you'd be scratching your head like, well, do they really know that stuff? Did they do it on a separate paper? Or did they look over their neighbors and got the answer? You just don't know. And so the safest thing to do is work out the math. Yeah. Okay, anything else? Okay. Yeah, and this practice exam right here is actually a part of, okay, so let me put it this way. The practice exam will cover the topics and it'll resemble a lot of the homework that we've had, but it's also a nice opportunity to even give a different flavor of some of the concepts too. So what that means is that when you prepare for the real exam, what you would want to do is look over the practice exam too, as well as the homework problems, right? Because I might find like a really neat way of covering one of these other topics in a certain problem that is unlike the homework problem that you guys have had. Okay, and also what these exams are, it's like a small sampling of what you guys have experienced already. So because you guys don't know what's going to be in the exam, you don't know the exact problems that's going to be covered, then that sort of forces you to cover everything, to study all the problems that we've had. And that's the point, right? Just like when people do polls on the national average or something like that, they don't poll everybody. They only poll like a certain number of people, and then they think, okay, well that's a good sampling of how the whole nation feels about certain things. That's what exams are like. Oh, and this red line here, if you remember, this red line corresponds to a break of like a week or something for Thanksgiving or something. So we'll have to decide if we want to have the practice exam on the weekend before the break or the weekend immediately after that break. But anyway, that's what that red line is for, so much wondering about that. Okay, so moving right along. So for review, yeah, so this was lecture 7. We had some amplifiers that were in terms of series shunt, series, shunt, or shunt series, right? And then we were able to apply this to all of them, right? And get the gain, look at the loop gain, the short circuit loop gain, open circuit loop gain, and also apply Blackman's theorem right here to find out what the resistance is looking through any type of port. And by the way, okay, so from the way I read the book, it just doesn't apply to this input and output. It could be any port, like any two connections to an amplifier. You can apply this. That's how the book reads. Okay. But of course, we applied it to the input and output because those are the most important things usually. Okay, so for last lecture, we also looked at voltage injection and voltage and current injection. And these methods were given to you because a lot of times you actually need the feedback, because the feedback is actually integrated, an integral part of what you're trying to do with your circuit. And so if you were to break this loop path in order to like measure things, it would sort of like interfere with the output of what the input was, so you wouldn't get a really good, honest answer for what you're looking for. So one way to do that is just inject a voltage along your feedback loop line. So it's still doing its thing, right? And also do the current and inject the current into that from external. And then by doing that, you're able to measure your voltage immediately on this side and your voltage immediately on that side, what you're applying. And for the current, you're able to measure the current I2 and I1, and those ratios, those were giving us our loop gain ratios. And actually, I'll go over that because we touched on it last lecture, but the problem was it was with me. I was a little confused about how the book was able to get the answer it got. So I did it, a way I would understand, and I'll show you guys. But yeah, so also we looked at this right here, looked at attenuation. So this is for like noise suppression. So you do have some distortion, like it can be modeled like this, where that part right there is your distortion. Wait, this little E right here is supposed to be attached to that. Okay, figure out how to fix it. Yeah, I'll fix that. So this is some distortion that's modeled right here. And so if you look at your voltage output right here, you have this coefficient, which is being multiplied by your input, and that's what you want. But also you have this source of distortion, this noise right here, and it's being attenuated much larger, more than this right here. So what's happening is that this amplifier is actually reducing the amount of noise that passes through. Well, at least from this, the distortion aspect from this type of input output of the output. Okay, so here are the concepts we're going to cover this lecture. So we're going to look at DC error sources. We're also going to look at common mode rejection and input resistance. And these are just the subcomponents of these kinds of common modes right here. Okay, so first let's go through the loop gain. All right, so so what we were told to do for the book was choose any arbitrary point P in the feedback and inject a voltage Vx to get this loop gain V, and inject a current Ix to get this loop gain I, Ti. Okay, so now, so this is what the book gives you right here. And this is the part where I didn't quite understand, actually. And the reason why is because if you look at V1 right here, and you look at I is clearly in this direction. And very little I goes up this direction. And if that's ideal, none would go up that direction. But very little I goes in that direction. So the majority of the I, and you can estimate with good approximation that I itself just goes through here. If it does go this direction, then I don't understand why there's a negative there. So that is the first part that confused me. Also, the other part that confused me was this expression right here, because here's RA, that's RA, so that means this expression right here must be negative I. But I don't see how I, even if it's positive I still don't see how, like, I don't understand this voltage drop, right? It looks like the entire resistance, there are these two in series, RA and RB, but I don't understand the voltage drop though. Because the way I'm looking at this is RA is like if you're right here and you're looking this direction to the left, what you'd see is some RA, regardless of what this is. So, but you're at this voltage right here, and this voltage right here is that voltage plus Vx. So this voltage right here is V2 plus Vx. If you want to include both of these, it seems to me that you would need a voltage that's beyond RA, like down here, but that would be 0. If you go up there, well, you can't go up there because there's no resistance going that direction. But so we're talking about this direction right here, or maybe this in parallel to that, because this path is parallel to this path right here. You guys see that? So but clearly that right there is talking about just these two in series, not including that one in parallel with that R1. So I don't know. Can anyone see something I'm not seeing here? Yeah.
I mean, it looks like you might have a voltage divider with A and B there, but that's about all I'm seeing.
It kind of looks like you're doing voltage division for V1 where you have, in the form of resistance over RA plus RB times some V, and then you replace that top R with possibly V over I. So it negates the I and then subs it
The only thing I think here is that VX minus AV1 is some node voltage in this circuit, and that you're dividing across R, A and RB resistors somehow.
Yes, yeah, so you're thinking that this piece right here is like voltage division,
Yeah.
and this is like the voltage.
Oh, it's
So
node.
yeah, so where is that node at? Like Vx minus AV1 V1. Where is that voltage at?
I would assume it's that black dot on the left there.
Right here?
If I had to guess.
No, that is V1.
Oh, wait, you're right. Okay.
What percentage did that again?
What was the question? What-
Is it possible that to be out?
Is A the gain?
Yeah,
Isn't it?
A is the gain of the op amp.
That's V out, right?
So
Yeah, I guess so.
wow, this.
Weird circuit stuff.
Okay, if anyone, okay, so we'll go ahead and move on, but if any, I like the voltage gain idea, but I still can't see where this is at. But if anyone sees it, let me know, because I was spending an hour trying to look at this. but anyway, so this is what I did right here instead, and so for this V1, I said it's equal to positive I, because it's that direction, times RA. And then I said this I right here is really this voltage minus that voltage. So the voltage right here, which is this negative AV1, minus this voltage right here, to just cross this resistor, times our RA. And then so here's the book analysis right there. That's the equation for the last slide. Here's the equation for the last slide right there. This is what the book does to end up with this, which is really the same thing that's over here. I mean, the end result's the same. So it's really bothering me now.
If you go back to that last slide.
Uh-huh.
So if I had to guess, so I think it's been commonly known as VID, voltage across the two terminals on your op amp. Would that not have to be equal to negative V1, in which case your output on your op amp voltage-wise would be negative AV1? So to get the voltage at V0 would be Vx minus AV1 using KVL.
The voltage across the op amp is V1, right?
Negative
Negative V1.
Yeah.
So the gain is negative A times V1. Or the output is negative A times V1.
Yeah.
Then
Yeah, I agree with that, yeah.
KVL would be Vx minus AV1 to get V out. So it's just voltage division on your output voltage across the A and B resistors, it looks like.
So you're saying that this,
That term is your voltage from your negative terminal of your op amp to the output.
right here?
Yeah.
And okay, so what's this voltage right here? What you're saying?
So from that positive negative terminal would have to be negative V1, would it not, to satisfy KVL between the two grounds?
Well, I'm not following you. What terminal are you talking about? This one or this?
So say you're going from that top left ground to the bottom right ground.
The top left ground, right here?
Yeah.
Okay.
So to maintain zero voltage between those two, you'd have to have a negative Vx, or a negative V1 term there, right?
Oh, so okay, so you're saying that So yeah, that's ground, that's ground. This right here is V1,
So,
right here, right?
yeah, so you have to have negative V1 across
So-
those two terminals.
Yeah, and so that's why this node right here is negative AV1.
Yeah.
Okay,
And then-
I understand that, okay.
If you go from that ground to V out, the voltage between them.
Wait, if you do what?
So you want the voltage to be out, the voltage reference to ground would be V1 plus that output of your op input and on, which in this case is negative AV1. So that would be, so that Vx minus AV1 is your V out, or VO, whatever you want to call it.
Tell me, like, show me after class.
Okay.
Because
I'm
I'm
not
still
entirely
not.
sure I'm going the right direction here for that.
I mean, it sounds plausible, yeah, but yeah, let's work it out after class, and then we'll
Okay.
yeah, present it the next day. Yeah. Okay. So, yeah. So anyway, so these were the two answers, and they're the same. It could be that this is correct, but I still don't know the reason for the negative I. But even so, anyway, for what I did here is that this I right here is this and this side. This I right here is that and that side, and you set them equal to each other. And what you're really looking for is a ratio of V2 to V1. This negative is because it's negative feedback. Okay, and then this is what you get right here. Yeah, so we won't see it here yet. But what you can do here is you can take this A, which came from right there, and you can multiply it and divide it by beta. We know that this A beta is really T. And we know that this 1 over beta is this expression right here. So if you plug those in, you get this expression, which is the same as this expression right here. See it? So that's for TV. And then this for current injection. This is actually, I do agree with the book right here. I can follow, right? Like this current, this T right here is this voltage, the Vx, minus negative A Vx. And so right here, you get that. And then this right here is negative, is feedback. This I2, that's negative because it's going the opposite direction over I1. So that negatives cancel, you get this. And then the same thing applies. You have your A, you have your beta, 1 over beta. You replace that with T, you replace your 1 over beta with this expression right there, and then you get that. And it looks pretty similar to the last one. So here's what we got for the first one from voltage injection. Here's what we got from current injection. And the unknowns you're solving for are the loop gain T and this ratio R B over R A. And that's what you get here. And remember, this is the loop gain. So if you're doing this experimentally, this ratio and that ratio is what you're measuring with your, your equipment. And that ratio of TI and that ratio of TI you're measuring with your equipment. So you just plug it into this equation, then you get the entire loop gain for the feedback. Okay. I'm not sure why you need that, but this is what you're really after right there. Okay. Yeah.
So how do you determine that TI is I2 over I1?
Wait, how what?
Like, why is TI I2 over I1 in this case?
Oh, this right here?
Yeah. Like, how do you get to that point?
Oh, this is like the loop gain. So it's like output over input.
Okay, so but how do you determine where the output versus the input is?
Oh, you mean like if you're doing this experimentally?
No, like just how how do you choose like a point where you consider an output and input and?
Oh, yeah, that's this arbitrary thing is the part that they're, I think you have a question with, right? You know, arbitrarily choose a point P
Okay.
in your loop, and then what they're trying to say is it doesn't really matter where that is, just that's where you would insert your voltage,
Okay.
your test voltage and your test current. But it's very general.
Okay.
Yeah.
But,
Yeah, but this is very similar to like what we had here, where we had the V2 over V1, and then you had your I2 over I1 for your input and output for your currents and voltages.
so in this case, you're arbitrarily choosing that node right above the current source. And
Oh yeah, well
input
that
and
node,
output.
yeah. Here's what I understand is that you can arbitrarily choose this P, but the P has to be the same for both the voltage and the current.
Okay.
Like you inject them at the same point, but that point can be anywhere along your path.
But that's both the input and the output in this case.
What was that?
Like, isn't gain the ratio of the output to the input?
Yes.
Okay, so that's both your output and your input at that point.
Yeah, just for that point right there, exactly. And then what we've done, we've associated it with the T, the entire loop gain, by forcing this A to be A beta, and that's how we're inserting that T there,
Okay,
and that's how we're getting that out.
So what's stopping me from defining Ti as I1 over I2 then?
Oh, taking the other ratio?
Yeah.
Huh. So I guess what you're saying is, why do we consider this as the output, and why do we consider this as the input instead of that? The
Yeah,
output.
so I'd just be just rather confused on this whole.
Yeah. No, that's a very good question, because if we're looking at the loop going around this direction, it seemed like anything on this side would be the output. I'm sorry, anything on this side would be the input, and anything on that side would be the output. Yeah, so for that question, let me, I'll ask on that one and get back to you.
All right.
Because that's a good
Not a problem.
point, like why,
It just seems like whenever T shows up, I'm not entirely sure how you calculated it or where it's come from, so I was just kind of curious.
well, yeah, that's a totally valid question, like why are we choosing that as the output and that side as the input when you're going in this direction? Yeah, that's a valid question. Okay, so, okay, yeah, so we went over that. So this next part right here is we're gonna look at this offset voltage. And so, if you remember back in lecture 2, we talked about this right here, where here's like the diagram for, you know, the behavior diagram for the op amp, where here's VID, here's the output. So remember, VID is the voltage between here, and here's the characteristic of what this behaves like, and it doesn't necessarily go through 0.00, which is a problem a lot of times. We know that it goes low as this and as high as that, right? But here's the questionable part right there, which is this offset. So we're gonna look at that. Okay, so what we're gonna do is take the op amp, and as you guys have seen, you know, we started off with the ideal op amp, and then we started adding more and more non-idealities to it. Okay, so here's another one. So the voltage across here is not exactly the same. like that voltage is not necessarily that voltage, right? And so so we know this ratio right here. So let's say we have some offset voltage here. The output of that would be that offset voltage multiplied by the gain of the op amp, right? So if you look at the op amp, I mean the offset voltage is the output over the amp, over the And if you want to measure that, the best way to do that is you just use a voltage follower, right? You have this going in, this is ground. This should be ground on an ideal output, on an ideal amplifier, but if it's not ideal, it's not going to be ground. It's going to be slightly higher or slightly lower. Okay, so you take this voltage and then you're having it be attached to the output. So that's the feedback loop right there. And then it then allows you to measure that voltage. And this voltage now, you'll see what your offset voltage actually is. Okay. Another way to model that is just say this. Let's say this offset voltage is really your ground plus your offset voltage going in. So that's another way to measure that. And what you can say is like your output voltage here is like your amplification plus these two added together. So it's this voltage across that plus your additional voltage coming in. That's one way to do it. Another way to do it is do your analysis here, and then you'll determine what that is. And of course, this can be positive or negative. So how to deal with that in the lab, in real life, here's your op amp. It's like a 741. And here's your potentiometer. And so you would connect your potentiometer. There's actually ports here for this potentiometer to connect to. And what you do, you adjust that until your offset is 0. Try to get that as close to 0 as possible. Here's a typical range for the offset voltage. It can go as small as like microvolts or as high as millivolts. Okay, so that's typically the range, but then again, you want to try to offset that to 0. And I believe the manufacturer, they'll tell you like the magnitude of it. They won't tell you the sign. It'll be positive or negative, and you'll just have to figure that out. But they'll tell you like at least the maximum value that it should be for that particular product. Okay. And here's what the connectors look like on this op amp. So here's 741. Here's what the connections are like. And so what you'd want to do, so here's your VCC and VEE right there. Here's for your offset, right here. And that's how you connect those two together. Everything else is just your inverting, non-inverting nodes, and your output. Okay. Now, also in the real op amp, you have, this is of course bounded, right? You go as high as that or as low as that. But even these values in on many op amps, you really can't get to those values. Like a typical case might be something like this, where they'll say your negative VEE plus 1 is the smallest you can get to, right? And the highest you can get to is your VCC minus 2 volts. That's as high as that op amp is going to give you. And then, so that's like the real range. But again, the specifications will give you that value. And also, the current coming out of the op amp there is a maximum that can come out of here. And it really depends on what the load is and the feedback is, right? So there's a certain amount of amps that they're able to come out, and it depends on what load is there. So you have to like know your load, know your specifications, and then try to match those together. Oh wow, still. Okay, I heard zippers. Yeah, I just have to go over the next stuff on Wednesday. Okay, slides 14. All right, so I'll see you guys on Wednesday.